Hey guys, so today I'm going to bring you a short and sweet, well hopefully short and sweet little tutorial on how to interface these sort of incremental rotary encoders with the microcontroller. And here's the specific one that I'm using. Let me go ahead and zoom into it. Turn that around for you so you can get a look at the model number. I will post this on my I'll post a link to it. I got it on Amazon, and it only has 4 leads that come out of it, and this is how they're wired to the microcontroller itself. There you go. Okay, so you see over here the red and ground are for 5 volts. It does require 5 volts, and then the other 2 lines that come out of the encoder are this green and white wire that you see right here, and they need to be pulled up to 5 volts via some resistors, and that's what I've done over here. That's what these 2 resistors do, and from that same node is where you're gonna get the signal to your microcontroller to read the pulses. And I have it wired up to B, if you can see that, B6 and B7, right? Doesn't matter which one you wire up to which pin, as long as you go one to each. And the interesting thing is about this is that it turns out that the STM32 the timers have a mode called encoder mode, where they count the pulses for you. It counts the pulses for you, and it also determines which way you're turning the shaft. If you're turning it this way or if you're turning it that way, and then it increments or decrements the counter register depending on how many pulses it's getting, and depending on which way you're turning, it will either increment or decrement. And this is that's in fact how you implement one of these, but usually you do it in code. But it turns out that the timers in the microcontroller have their own hardware stuff going on to do this. And like I've been implying to you guys a lot, that if you can offload anything to the hardware, then by all means do it, because that's less code you're gonna type. The hardware is gonna do it faster than the software, because in software you've got to increment the variable, you got to jump into an interrupt routine, you've got to do all kinds of stuff that takes time, while the hardware is it's going to do it a lot faster, and it's just going to update the register with the count, and that's it. If you know anything about these how these incremental things work or not, then here's a quick picture I found on GitHub. Basically, you have those 2 wires I showed you, the white and the green one, and one of them will correspond to this sort of pulse, and the other one will be the other sort of pulse. And basically all they're the same pulse, it's just they're out of phase, right, as you can see here. And if you were to read this from left to right, then if you look at it like that, this appears to be a rising edge, then it's high, and then this is the falling edge, right? However, if you read this from right to left, then this appears to be the rising edge, and then it's high, and then this appears to be the falling edge. So depending on which way you turn that shaft, that's how your microcontroller is gonna read it. Because if you turn it one way, it's gonna have this sort of scheme. If you turn it the other way, it's gonna look like this, right? So that's all it does, and all it's doing is really comparing one to the other. For example, if you have a rising edge on this, let's pretend this is the green wire and this is the white wire. So if the green wire is goes high, while the white wire is low, so that means we're going in this direction, right? So the green wire goes high while the white wire is low. But if we're going in this direction from white to left, and we think of that same logic, this time the green wire goes high while the white wire is high. So boom, goes down low, green wire goes high, white wire is high. So it depends on which way you look at it. Now the hardware timer, what it's going to do is you can set it up where every time this goes high while this one is low, it increments the counter, right? So it's going to increment here and it's going to increment here. You could also have it increment on the bottom wire, where when this one goes high and this is high, it increments by 1. So it's going to increment here and it's going to increment here. Or you can have an increment on both edges. For example, you could have an increment on the rising and the falling of just this one, or on the rising and falling of this one, or on the rising and falling on both. So you have an increment here, increment here, increment here, and increment here. What does that mean? That means that since this is a 600 pulse per revolution, in other words, every time you turn this shaft 360 degrees, you're going to get 600 pulses. But that's using it in a normal mode where you're just counting the rising edge of one of the signals compared to the other, right? But if you count both edges of both signals, you actually quadruple your resolution. So instead of 1600, this is going to be 2400 pulses per complete revolution of the shaft. So let me go ahead and take you to the data sheet and kind of show you what's going on here. So I found this feature on both the general purpose timers 2 to 5 and on the advanced timers, as you can see, encoder mode, right? So for my example here, I used the general purpose timers 2 to 5, and if you go down to where it says functional description, you go down to this section where it says encoder interface. Again, it's under functional description. Ultimately, this tells you that this basically all it's doing is every time you turn this thing, every time it sends it a pulse, it increments the counter value in the counter register. And then it also tells you that the DIR bit in the control register 1 will tell you which direction you're turning, right? And this is all the, I guess, the truth table for these things. And again, you can have it count on just one or both rising or falling edges. That's all this table is telling you. And here basically it tells you what you need to do. So let me get my thing here out of the way, because I wrote this down in my blog, and you can go ahead and look at it in my my blog. Alright, so this is the first thing you're going to do, and all this these two little bullet points here, what they do is that they match the channel 1 and channel 2 inputs to timer 1 and 2 inputs. Not timer 1, but timer 1, channel 1 and 2 inputs. So you're just mapping the channels to the timer, right? If that makes any sense. So again, all the code that I needed to do, I really just got from reading this data sheet, and I didn't even understand exactly what it did. I just copied it, and then it worked, and then I kind of looked into it to see what it does. So again, we're mapping channel 1 and 2 inputs of the actual the pins, right? This right here represents the pin, and we're mapping those to channel 1 of the timer and channel 2 of the timer. Okay, now these two bullet points, they set up the actual channels as non-inverting, so a rising edge will be seen as a rising edge. Alright, so that's all that does. And these, as you can see, they're all 0, which this is for channel 1, this is for channel 2, the polarity for it. They're all 0, and they're all 0 by default, so you don't really have to do anything. Now these SMS bits, they control what you want, when you want it to increment. Do you want it to increment just on the rising edge of one channel, the rising edge of the other channel, or both rising and falling edges of both channels? So you configure these SMS bits in this SMCR register, and ultimately then you just enable the channel. And since this is it's a timer, you don't have to set the prescaler or anything, because remember that controls the frequency. But since you turning the shaft here, that is basically, how fast you turn it is the frequency. There's no real up counting or anything that needs to be done. So you don't even have to worry about the prescaler or anything of the timer, because we're not running it automatically. We're just incrementing the counter based on these pulses. So there's nothing to worry about any other settings. The only other setting you do have to set is the auto reload register for the timer, and it's this register here, and this is, again, it's 16 bits, and the only thing this is going to control is how high it counts, right? So the maximum number that can fit here is 65535. In other words, in hex it's FFFF, and that's how high you can allow it to count. Now if you only wanted to rotate this and count up to just 1,000 or just 100, then you would set this at 100 to 100, and it'll just count up to 100 every time you turn it. And it overflows by itself. So once you reach 100, it goes back to 0. Or if you're going the other way, you're counting down. Once you reach 0, it overflows around to 100. And if you don't like that kind of behavior, you can take care of that in your code. So that's really all that's into it. The pins that it uses have to be set up as input floating, which is the default for GPIOs. So basically, again, you don't have to do anything for that part. My connections here on the breadboard, just like I showed you, the white and the green wire are being pulled up to 5 volts, and that same node is being read by pins B6 and 7, which correspond to channels 1 and 2 of timer 4 is the one that I used. And all the other connections are just the ST-Link and the USB to serial converter, so we can see the output on the COM port. So this is how I have two versions. I have the regular interrupt version that I implemented using interrupts, which I'll show you how that works in just a second. And then I have this timer hardware version that I implemented. So first, I guess first let me show you how this interrupt version works, because you can do, again, either version, and I'm gonna uncomment that and comment this one out. So we go ahead, that's loaded, we're gonna upload it, it's complete. We pull this guy out, turn it on, and I'm gonna press reset, and it should start printing. And as I turn this, okay, I forgot the interrupt version. I use pins B0 and 1. Those are the interrupts I used, so I have to switch the pins here. Alright, so now as you can see, as I turn it, it's going down to negative, but then I turn it the other way and it's going to go back up to my positive numbers, and then just keep incrementing and incrementing. If I reset this, because I want to see the resolution here, so it's at basically 1. If I turn it 360, I have a resolution of 1200. In other words, I'm counting the rising edge of both phases, both signals. So I get a resolution of 400. And if I wanted to count the both edges of both signals, then I would have to adjust my code. But I only counted the rising edges of both signals. So that interrupt version, obviously, it just involved setting my pins into alternate mode and turning on the interrupts and all this stuff. I'm sure you've seen my videos on how to set up interrupts on the GPIO, so I'm not going to really explain this here. And then here are my interrupt handlers for both pin 0 and 1 on port B. And then all I do here is, if this is the interrupt for pin 1, then I check the interrupt for pin 0. I check the state of pin 0, right, and to see if I'm going in one direction or if I'm going in the other direction, and depending on that, I will increment or decrement this variable called val. And I do the same thing with the interrupt for pin 0. I check the state of pin B1, and depending on what that state is, I know if if I'm going in one direction or the other, so I increment or decrement. But as you can see, every time I turn this thing and it pulses, I'm interrupting my microcontroller. My microcontroller then has to go from thread mode to handler mode. Then it has to come into these things. It has to do this, clear the flag for the interrupt. It has to check this thing. It has to either increment or decrement this variable. Then it has to get out, only to again have to jump to this other one, and you know what I mean. So you're interrupting your code, your processor constantly. You're having to do this stuff. Now this is not really math intensive stuff here, but nevertheless you're using your CPU resources, right? However, with this, and then I'm printing it, but that's just necessary evil there. Now when you use the other mode, the hardware mode, right? So here I'm going to use hardware mode, hardware timer. So I'm calling this function. Alright, so now let's get into this and see what I did here. I obviously enabled GPIOB, and let me switch my pins back to 6 and 7 before I forget. Okay. So I enable also timer 4. Now the pins have to be input floating, and that's the default. So I just left it. I didn't write anything. I mean, you could for sanity's sake. So yeah, that's default. So I didn't have to adjust the pins or anything. You don't even have to do alternate function because it requires to be input floating, and that's the reset state. So you're good. Then I reloaded into that auto reload register the maximum value that I wanted to count up to. And then I did the steps that the datasheet told me. I did this whole, basically all these steps. If I could go into my encoder mode, and let me close this. Whoa, I did not want to do all of that mess. So whatever this thing, these steps right here, that's exactly what I did. Where I mapped the thing, set the mode. The mode that I set was so that it could count on both edges of both signals. So you can see these bits right here. Let's open this up. Where is my CCMR1? Is that it? Nope. Here, the SMS bits. If we go down to those bits, you can select to count up and down on the edges of the channel 1 or channel 2, whatever the hell you want to do. I put both. It's going to count up and down on both edges of both signals. So I did that here, and then ultimately I enabled it. Now this is all the code that's required. There's no interrupts, nothing. I just configured a timer to do that, and that's it. All I'm doing here is printing the value of the count register on timer 4, and I'm using this here. So let's go ahead and build that, and go here, open up my COM port, clear this, reset the thing, and as I turn it, you'll see that it's going up. It's gonna go all the way up to 65535, and then it's gonna overflow down to the bottom once I could get it up that high. Okay, that'll be a while. There you go. It just overflowed. So there's it is at the 65,000 range, and then it overflows to the bottom. And then again, if you go down, you can have it overflow the other way around if you turn it the other direction. Now the cool thing is this is all going on in hardware. As you can see, there's no I'm not calling any interrupts because those interrupts are set up in here, so they're not even set up right now. I'm just, all I called was this function, was just set up the timer, and there's no math, nothing going on, no interrupts, nothing. My while loop is just running by itself. So you could even take this a step further and use DMA and have it grab this value from here and stick it into a variable, and anytime you check that variable, you know you're gonna have the current position of the rotary encoder. So yeah, so that's pretty cool stuff. I thought it was pretty neat. I'd never seen that feature before, and I haven't even seen anybody on YouTube do it this way before. So I thought that was pretty cool. Let me see if I'm forgetting anything else. That's pretty much it, guys. So give that a shot. Play with it if you have any use for rotary encoders and all that great stuff. And let me know if I missed anything. Don't think I did. But yep, enjoy.